The group 1 of the periodic table comprises of 6 elements: lithium, sodium, potassium, rubidium, cesium, and francium, besides hydrogen, which is not a member of the alkali metal family. It has been included in group 1 because of its similarity with the electronic configuration of these elements. These are called alkali metals since they readily dissolve in water to form soluble hydroxides, which are strongly alkaline in nature. All these elements are typically metals.
ਪਿਆਰੇ ਵਿਦਿਆਰਥੀਓ, ਅੱਜ ਦੇ ਪਾਠ ਵਿੱਚ ਤੁਹਾਡਾ ਸਵਾਗਤ ਹੈ। ਸਾਡਾ ਅੱਜ ਦਾ ਵਿਸ਼ਾ ਆਲਕਲੀ ਮੈਟਲਸ ਹਨ, ਪਰ ਅੱਜ ਦੇ ਇਸ ਪਾਠ ਬਾਰੇ ਹੋਰ ਵਿਚਾਰਨ ਕਰਨ ਤੋਂ ਪਹਿਲਾਂ ਆਓ ਅੱਜ ਦੇ ਪਾਠ ਦੇ ਸਿੱਖਿਆ ਉਦੇਸ਼ਾਂ ਨੂੰ ਜਾਣ ਲਈਏ।
Upon completion of this topic, learners will be able to write electronic configurations of alkali metals, discuss abundance and occurrence of alkali metals, discuss physical and chemical properties of alkali metals, list properties of alkali metals.
Children, let's first discuss abundance of alkali metals in nature. Sodium and potassium are the most abundant elements, whereas lithium, rubidium and cesium have low abundance. Francium is a radioactive element. Occurrence: lithium. It is found in small amounts on the Earth's surface. It mainly occurs in the form of silicate minerals as lepidolite, that is LiAlSiO3FOH whole twice. Sodium. Sodium is the seventh most abundant element on the Earth's surface. It exists as sodium chloride. Potassium. Potassium mostly occurs in the form of the chloride as potassium chloride. It remains present not only in the seawater but also as a mineral known as sylvite on the Earth's crust. Francium. Francium is a radioactive element with a very small life period of about 21 minutes and is one of the rarest elements on the Earth's surface.
Electronic configuration. Students, we are looking at a table showing an element, its symbol, its atomic number, and its electronic configuration. Element lithium is shown by symbol Li. Its atomic number is 3. Its electronic configuration is 1s2 2s1. Its electronic configuration with inert gas core is also shown on the screen. Sodium is shown by symbol Na. Its atomic number is 11. Its electronic configuration is 1s2, 2s2, 2p6, 3s1. Its electronic configuration with inert gas core is also shown on the screen. Potassium is represented by symbol K. Its atomic number is 19. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Its electronic configuration with inert gas core is also shown on the screen. Rubidium is represented by symbol Rb. Its atomic number is 37. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 5s1. Its electronic configuration with inert gas core is also shown on the screen. Cesium is shown by the symbol Cs. Its atomic number is 55. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p6, 6s1. Its electronic configurations with inert gas core is also shown on the screen. Francium is represented by symbol Fr. Its atomic number is 87. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f14, 5s2, 5p6, 5d10, 6s2, 6p6, 7s1. Its electronic configuration with inert gas core is also shown on the screen. If we look at the electronic configuration of all alkali metals, we find that the last electron enters into the s orbital in the alkali metals. Alkali metals are called s-block elements since the elements have one electron each in the valence s subshell of their atoms, that is, they have ns1 configuration where n represents the valence shell where n is equal to 2 to 7.
Physical properties of alkali metals. Now, let's discuss about the physical properties of alkali metals. Atomic volume. Alkali metals with lithium to francium atomic number increase ਕਰਨ ਨਾਲ atomic volume ਤੇ ਕੀ ਪ੍ਰਭਾਵ ਪੈਂਦਾ ਹੈ ਆਓ ਇਸ ਤੇ ਵਿਚਾਰ ਕਰੀਏ The atomic volume of alkali metals increases with the addition of one extra shell with each succeeding element. Atomic volumes of the alkali metals are shown on the screen. It has been depicted in cubic centimeters. For lithium element, atomic volume is 12.97 cubic centimeter. For sodium, atomic volume is 23.68 cubic centimeter. For potassium, atomic volume is 45.36 cubic centimeter. For rubidium, atomic volume is 55.80 cubic centimeter. For cesium, atomic volume is 69.95 cubic centimeter. Atomic and ionic radii. The alkali metals have maximum value of the atomic radii or metallic radii in the respective periods, and these values further increase down the group. Let's have a look at a table showing atomic number, metallic radius in picometer and ionic radius of cations in picometer of the alkali metals.
From lithium to francium down the group, the number of energy shell increases by 1 with each succeeding element. Screening effect of the inner filled shell on the valence electrons increases. Electron cloud tends to expand, but nuclear charge, which also goes up from lithium to francium. This tends to decrease the atomic radii by attracting the electron. But screening effect overcomes the contractive effect of nuclear charge, thus atomic radii increases down the group. The increase in atomic radius as we go down the group from lithium to cesium is primarily due to the predominant screening effect of inner filled shells on the valence s electron. Alkali metal atoms form monovalent cations by the loss of valence s electrons. The cationic radius is less as compared to corresponding metal atom due to contractive effect of the increased nuclear charge and lesser number of energy shells.
Ionization enthalpy. First, ionization enthalpies of the alkali metals are the lowest because noble gas core shields the lone s electron in the valence shell from the direct attraction of the positive charge on the atomic nucleus. As a result, the valence s electron is loosely held by the nucleus and can be easily knocked off by supplying only small amount of energy. The ionization enthalpies of alkali metals decrease progressively as we move down the group from lithium to cesium. Due to an increase in the number of inner shells, the screening effect also increases. As a result, the attraction of the nucleus for the valence s electron decreases. The second ionization enthalpies of alkali metals are very high because the monovalent cations have the stable noble gas configuration and it is difficult to remove an electron from the stable noble gas configuration. The second ionization enthalpies decreases from lithium to francium due to increasing size and increasing shielding effect. Oxidation states. All alkali metals have NS1 electronic configuration. All alkali metals have only one valence electron. These alkali metals have strong tendency to lose its single valence electron to acquire the nearest noble gas configuration. The first ionization energies of these elements are very low, so they exhibit an oxidation state of +1 in their compounds. Alkali metals form monovalent ions. Alkali metals are thus strongly electropositive in character and form ionic compounds. This electropositive character of alkali metals increases down the group. Let's have a look at the unipositive metal ions of lithium, sodium, potassium, rubidium and cesium. The second ionization energies are very high because monovalent cation has noble gas configuration, so it is not possible for the metals to form divalent ions in any of their compounds. Thus, alkali metals are univalent, show only +1 oxidation state and form only ionic compounds. Hydration enthalpy. Hydration enthalpy is the amount of energy which is released when the ion of a particular element takes up molecules of water and gets hydrated. In general, smaller the size of the ion, greater is the magnitude of charge, more is its tendency to get hydrated or more is the hydration enthalpy. In alkali metals, the hydration enthalpies of the monovalent cations are low due to their large size. The hydration enthalpies of alkali metal ion decrease with increase in ionic sizes. Hydration enthalpy of unipositive lithium ion is greater than hydration enthalpy of unipositive sodium ion, which is greater than hydration energy of unipositive potassium ion, which is greater than hydration energy of unipositive rubidium ion, which is greater than hydration energy of unipositive cesium ion. Let's now learn about electronegativities of alkali metals. Alkali metals are highly electropositive, which means they have a tendency to lose electrons. But if we discuss electronegativities in them, we find that their electronegativities are very low. It means that they have very low tendency to attract electrons. It shows that electropositive tendency is just opposite to electronegativity nature. Electropositive character increases from lithium to cesium, whereas electronegativity character decreases from lithium to cesium. Electronegativities of lithium, sodium, potassium, rubidium and cesium are 1.0, 0.9, 0.8, 0.8 and 0.7 respectively. As alkali metals have low ionization energies and low electronegativity, all alkali metals and their salt impart characteristic color to the flame of the burner and exhibit photoelectric effect and form ionic compounds. Let us first discuss the characteristic flame coloration in the alkali metals. Characteristic flame coloration ਵਿਦਿਆਰਥੀਓ ਜਿਵੇਂ ਕਿ ਤੁਸੀਂ ਜਾਣਦੇ ਹੋ ਕਿ alkali metals ਦੀ ਬਹੁਤ ਘੱਟ ionization energies ਹੁੰਦੀ ਹੈ. When alkali metals are kept in the flame of a Bunsen burner, it provides sufficient energy to excite the electrons to higher energy levels. But electrons in the high energy levels are not stable. That's why after some time these excited electrons return to their original energy levels. In this process, they emit extra energy in the form of electromagnetic radiations which falls in the visible region of light and gives characteristic flame coloration. The different colors of the alkali metals can be explained on the basis of amount of energy absorbed for excitation of the valence electron. Lithium, sodium, potassium, rubidium and cesium salts on heating on flame imparts crimson red, yellow, pale violet, violet and bluish color. Have a look at the different wavelength of light absorbed on the screen.
Let's take sodium carbonate salt. Presence of sodium gives golden yellow color to flame. Next, let's take potassium dichromate salt. Presence of potassium gives flame of pink violet color.
Photoelectric effect. आओ ਹੁਣ photoelectric effect ਤੇ ਵਿਚਾਰ ਕਰੀਏ. ਜਦੋਂ electromagnetic radiation alkali metals ਦੀ ਸਤਹ ਨਾਲ ਟਕਰਾਉਂਦੀ ਹੈ ਤਾਂ ਉਹ electrons ਛੱਡਦੀਆਂ ਹਨ. ਇਸ ਨੂੰ photoelectric effect ਕਿਹਾ ਜਾਂਦਾ ਹੈ. Low ionization energies of alkali metals allow the electrons to be easily ejected from alkali metals. When exposed to light, cesium has lowest ionization energy. That's why it can show photoelectric effect to maximum extent. Lithium, which has the highest ionization enthalpy amongst the alkali metals, cannot be used in photoelectric cells because it does not release electrons when exposed to light. Nature of the compounds. Alkali metals gives ionic compounds. They can lose valence electrons very easily and form cations. This is so because of two reasons. These have low ionization energies and large atomic sizes. Density. Alkali metals are very light. The first three members of the family are even lighter than water. The density of alkali metals increases downwards except for potassium metal. ਵਿਦਿਆਰਥੀਓ ਅਸੀਂ alkali metals ਦੀ density ਜਾਂ ਸੰਘਣਤਾ ਵੇਖ ਰਹੇ ਹਾਂ. ਇਹ lithium ਤੋਂ cesium ਤੱਕ ਵੱਧਦੀ ਹੈ except potassium. Metal density ਨੂੰ ਇੱਥੇ grams per cubic centimeter ਨਾਲ ਵਿਖਾਇਆ ਗਿਆ ਹੈ. This is because of their large size and their atoms are less closely packed and have low densities as we move down the group from lithium to cesium. Both the atomic size and atomic mass increases, but the effect of increase in atomic mass is more as compared to the increase in atomic size. Therefore, the density which is equal to mass per unit volume increases downwards. However, there is an exception. The density of potassium is less than that of sodium. This is due to the abnormal increase in atomic size of potassium. melting points and boiling points. Students, let's have a look at the table shown on the screen. We are looking at the melting points and the boiling points of alkali metals in Kelvin. For lithium, melting point is 453.5 Kelvin, while boiling point of lithium is 1620 Kelvin. Melting point of sodium is 370.8 Kelvin, while boiling point of sodium is 1154.4 Kelvin. Melting point of potassium is 336.2 Kelvin, while boiling point of potassium is 1038.5 Kelvin. Melting point of rubidium is 312 Kelvin, while boiling point of rubidium is 961 Kelvin. Melting point of cesium is 301.5 Kelvin, while boiling point of cesium is 978 Kelvin. We find here that melting points of alkali metals decrease from lithium to cesium. Here we see that the melting point and the boiling point of alkali metals are low and decreases with increase in atomic number because alkali metals have large size and weak intermetallic bonds. Metallic character. Group 1 elements are typical metals and are so soft that most of them can be easily cut with the help of a knife. The metallic character increases down the group. In the alkali metals, the kernels are of large size as it depends upon its atomic size and there is only one valence electron. Therefore, metallic bond is rather weak and as a result, alkali metals are quite soft. They can be cut even with a knife. Lithium, the first element, is the hardest since the kernel is the smallest in size.
Reactivity with air and moisture. When the alkali metals are exposed to atmosphere, air and moisture get converted into oxides, hydroxides and finally to carbonates. Thus, alkali metals get tarnished. Metal reacts with oxygen to form metal oxides. Metal oxide reacts with water to form metal hydroxides. Metal hydroxides react with carbon dioxide to form metal carbonates and water. Because of this reason, the alkali metals are stored in inert hydrocarbon solvents like petroleum, ether and kerosene oil, which prevent them from coming in contact with air and moisture. The alkali metals react with dry air and form their oxides. They burn vigorously to form their oxides. Lithium reacts with oxygen to form lithium oxide. Sodium reacts with oxygen to form sodium peroxide. Potassium reacts with oxygen to form potassium superoxide. Rubidium reacts with oxygen to form rubidium superoxide. Cesium reacts with oxygen to form cesium superoxide. Thus, reactivity with oxygen increases from lithium to cesium. The stabilities of these oxides are linked with the relative size of the cations and anions involved and also upon the charges present on them. A smaller cation can stabilize a smaller anion, while a larger cation can stabilize a larger anion. Paramagnetic nature of superoxides. Under suitable conditions, M2O, M2O2 or MO2 compounds may be formed. Superoxide ion has 3 electron bonds, so it has one unpaired electron which makes it colored and paramagnetic. Normal oxides of the alkali metals are colorless and diamagnetic.
Reaction with water. The alkali metal reacts with water to form metal ion, hydroxide ion and dihydrogen gas. If we represent alkali metal by M, we can write general equation as shown on the screen. Among alkali metals, hydrated lithium has the most negative standard electrode potential and hence the strongest reducing agent. Even then, lithium reacts with water less vigorously than sodium. Sodium has a low melting point and the heat of the reaction is sufficient to make it melt or even vaporize. The molten metal thus spreads out there by exposing a large surface to water. As a result, it reacts even faster, gets even hotter and catches fire. Lithium, on the other hand, has high melting point. Although the heat of the reaction is high, it is still not sufficient to melt the metal and hence the reaction proceeds gently. Alkali metal hydroxides are white ionic crystalline solids. These are shown with the help of formula shown on the screen. These are soluble in water. They all are deliquescent except lithium hydroxide. Their aqueous solutions are strongly alkaline and therefore dangerous to handle. They neutralize acids to form salts as shown on the screen. Aqueous solution of sodium hydroxide reacts with aqueous solution of hydrochloric acid to form aqueous solution of sodium chloride and water. Reactivity with hydrogen. The alkali metals react with hydrogen at 673 Kelvin to form metal hydrides, which are ionic in nature. Reactivity with halogens. The alkali metals react with halogens to form halides. Here, M may be Li, Na, K, Rb, Cs or lithium, sodium, potassium, rubidium and cesium, where X is equal to F, Cl, Br and I, or fluorine, chlorine, bromine and iodine. Generally, they form ionic metal halides. One exception is there. Lithium forms lithium halides, which are covalent in nature. The alkali metal halides are prepared by the reaction of appropriate oxide, hydroxide or carbonate with aqueous hydrohalic acid. Here X may be fluorine, chlorine, bromine and iodine. Alkali metal fluorides are more stable while iodides are least stable. Have a look at the comparison on the screen which shows that the melting and boiling points of fluorides are greater than the melting and boiling points of chlorides, which are greater than the melting and boiling points of bromides, which are greater than the melting and boiling points of iodides. Covalent character of lithium iodide. The chemistry of lithium shows some anomalies as the cation of monopositive lithium is so small it polarizes anions and so introduces a covalent character to its compounds. Let's discuss in detail.
Lithium iodide is covalent in nature. Do you know why is it so? It is so because lithium monopositive ion, that is Li positive, has small size and magnitude of positive charge, is quite large and has maximum tendency to attract an electron cloud of anion, that is iodide ion, towards itself. As a result, electron cloud of the anion distorts. The two oppositely charged ions come closer and their charge gets partly neutralized. Thus, covalent bond is formed. Therefore, lithium iodide is covalent in nature.
Reaction of solubility of alkali metal in liquid ammonia. Now tell me what happens when sodium metal is added to liquid ammonia. Sodium dissolves in liquid ammonia to give a deep blue solution of sodium ammoniated cations and ammoniated electrons. Have a look at the reaction shown on the screen. The solvated electrons give the blue color to the solution. Do you know why is it so? When light falls on the ammoniated electrons, they absorb energy corresponding to the red color and transmitted light has a blue color. This solution is also used as a reducing agent. Each of the dissolving sodium atoms loses an electron and becomes a cation. Both the cation and the free electron are solvated by ammonia molecules. At higher concentrations, the color of the solution changes to bronze due to the formation of metal ion cluster, and it conducts electricity like a metal. The electrical conductivity of the solution is because of the ammoniated cation as well as the ammoniated electrons. Reducing nature. The alkali metals are strong reducing agents. They have a high tendency to lose electrons. Lithium is the first element of the alkali metals. It is the strongest reducing agent because of its greater hydration energy. Let's discuss standard electrode potentials of the alkali metals. It lies between minus 2.7 volts to minus 3.0 volts. It indicates that these metals have a strong tendency to form cations in solution. They react with water to produce alkali hydroxides and hydrogen. Let us now have a look at the equations on the screen. Sodium metal reacts with water to form sodium hydroxide and hydrogen gas. This reactivity increases as we move down the group. Students, it's a time to check what we have learned so far. Let's do so with the help of a question. Why are lithium salts commonly hydrated while those of other alkali metal ions are usually anhydrous? Answer is, in lithium salts, the lithium ion due to very small size gets readily hydrated on coming in contact with moisture or water. Therefore, lithium salts are commonly hydrated, but the other alkali metal ions are comparatively bigger in size. They have therefore lesser tendency to get hydrated. These salts are usually anhydrous. ਬੱਚਿਓ, ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਅੱਜ ਦਾ ਇਹ ਪਾਠ ਕਾਫੀ ਦਿਲਚਸਪ ਲੱਗਿਆ ਹੋਵੇਗਾ। Thank you for your attention and see you next time.